Burbank, California. Advanced Development Projects Facility. March 1963. Dick Fuller is holding a stress analysis report. The numbers are clean. The conclusion is not. The titanium skin panels on the aircraft designated Article 123, what would become the SR-71 Blackbird, are cracking. Not catastrophically, not visibly. At the microscopic level, where fatigue failures always begin. The resonance frequency generated by the airframe at sustained Mach 3.2 cruise matches, almost precisely, the harmonic threshold of the titanium alloy panels at 600 degrees Fahrenheit skin temperature. The panels are destroying themselves. Quietly, predictably, inevitably. Fuller has 6 weeks. Clarence Kelly Johnson has already told the program managers, if there is no solution, the production line stops. We will come back to Dick Fuller and what he found in that data. But to understand why a materials failure in a California workshop nearly ended America's most consequential reconnaissance program, you need to know what the SR-71 was actually being built to survive. The year is 1958. The U-2 is flying. Gary Powers has not yet been shot down. That comes in May 1960. But the CIA and the Air Force already know the problem. A subsonic aircraft, no matter how high it flies, is eventually catchable. Soviet surface-to-air missile technology is advancing. The window for high-altitude, low-speed reconnaissance over denied territory is closing. Kelly Johnson and the Skunk Works team at Lockheed's Advanced Development Projects Division settled on one answer: speed. Fly fast enough that no missile in the Soviet inventory can achieve a valid intercept solution. That means Mach 3.2, sustained, at 85,000 feet, for hours at a time. At those speeds, the aircraft skin reaches 600 degrees Fahrenheit during cruise. Aluminum melts at 1,220 degrees, but loses structural integrity well before that, around 250 degrees. Steel is too heavy. Composites in 1958 don't exist in the form required. There is only one material that works: titanium. Here's where it gets strange. The United States in 1963 could not manufacture titanium at the scale, purity, or precision the SR-71 required. The domestic supply chain did not exist, and the primary global source of high-grade titanium ore was the Soviet Union, not a cooperative supplier for obvious reasons. The CIA ran a covert procurement operation. Front companies purchased Soviet titanium through third-party intermediaries in Europe and Asia. The metal that would allow America to fly over the Soviet Union at 3 times the speed of sound came, in significant part, from the Soviet Union itself. That detail stayed classified for 2 decades. The procurement problem had a solution. The manufacturing problem did not. Not yet. What struck me going through the declassified Skunk Works production records is how close the program came to a different outcome. The titanium alloy selected for the SR-71 skin, designated B-120, behaved differently at operating temperature than at ambient conditions. Every test, every simulation, every materials analysis had been conducted at room temperature. Nobody had adequately modeled what B-120 would do when the aircraft hit sustained cruise, and the skin temperature climbed past 400 degrees. Fuller's March 1963 fatigue test results gave the answer. It cracked. That matters because the SR-71 was not a prototype. By March 1963, 12 aircraft were in various stages of production. The tooling was set. The manufacturing processes were locked. Changing the attachment geometry, the way the skin panels connected to the titanium substructure, meant scrapping tooling that had taken 2 years to build. Fuller's team ran 3 weeks of accelerated fatigue testing. The cracking pattern was consistent. Stress concentration at panel attachment points, the rivets, the fasteners, the interface between skin and frame, was amplifying the resonance frequency rather than damping it. The panels were vibrating themselves apart at exactly the conditions under which the aircraft was designed to operate. The standard engineering response is to tighten tolerances. Make the connection stiffer. Reduce the degrees of freedom at the attachment points so vibration cannot propagate. Fuller's team tried this. The cracking accelerated. A stiffer joint transmitted more stress into the panel, not less. Nobody expected this. The solution was to loosen the attachment, deliberately, by 0.03 inches, 0.03 of an inch, at each fastener point. Enough clearance that the panel could move microscopically relative to the frame, dissipating vibrational energy as heat rather than transmitting it as stress concentration. In practical terms, the aircraft supposed to be the most precisely manufactured machine in the American aerospace inventory was redesigned on purpose to be slightly loose. The fix for a vibration problem was controlled movement, not elimination, accommodation. Here's the take that will generate disagreement. The SR-71 program's real achievement was not the aircraft. It was the institutional willingness to discard a correct engineering assumption, that tighter is better, when the data said otherwise. Most aerospace programs in 1963 would have spent another 6 months proving the original assumption was right. Fuller's team had 6 weeks and chose to trust the evidence. The loose panel solution had an immediate, visible consequence. The SR-71 leaked fuel on the ground. Substantially. The titanium skin panels were dimensioned to seal only at operating temperature, when thermal expansion closed the 0.003-inch gap. At ambient conditions, they sat slightly open. Pilots and ground crews learned to pre-flight the aircraft, knowing it would be actively leaking JP7 until it reached cruise altitude and temperature. That tells you something about the design philosophy. The SR-71 was not built to work at rest. It was built to work at Mach 3.2 and 85,000 feet. Every other condition was secondary. Put yourself in the position of the ground crew chief seeing this aircraft for the first time. Fuel pooling under a machine that is supposed to outrun every threat in the Soviet inventory. The natural response is, something is wrong. The correct response, which took time to communicate through the operational community, was, this is nominal. The aircraft works when it matters. Fuller's team had solved the immediate problem, but the cracking discovery had surfaced something deeper. The precision requirements for titanium machining at Skunk Works were unlike anything the American aerospace industry had encountered. Conventional cutting tools, high-speed steel, even early carbide, work-hardened the titanium surface during machining. Work hardening changes the fatigue characteristics of the material. A component that passed initial stress analysis would fail in service because the machining process had altered the material properties at the surface. The fix required a complete revision of titanium machining protocols, cutting speeds, coolant chemistry, tool geometry, depth of cut. All of it had to be recharacterized for B120 titanium at the dimensions and tolerances the SR-71 required. What came out of that process was the first systematic industrial body of knowledge about precision titanium manufacturing at aerospace tolerances. That knowledge did not stay classified indefinitely. Through technical publications, through engineer movement between programs, through the natural diffusion of expertise across the aerospace industry, it became the foundation subsequent programs built on. The program histories tend to understate what this means about the Cold War aerospace era. The SR-71 was not just an intelligence collection platform. It was an industrial forcing function. The requirement to fly at Mach 3.2 created manufacturing problems with no existing solutions. Solving those problems produced capabilities in materials science, in precision machining, in thermal management engineering that did not exist before the program began. The aircraft was the deliverable. The manufacturing knowledge was the strategic asset. Subscribe. Next week, we are examining the B-21 Raider's composite-titanium hybrid skin and the direct engineering lineage from Fuller's 1963 solution that Northrop engineers acknowledge in unclassified program histories. The connection is not metaphorical. It is documented. The B-21 Raider operates in a fundamentally different threat environment than the SR-71. Stealth, not speed, is the primary survivability mechanism. But the thermal and structural challenges of a low observable aircraft skin, operating under combat conditions, flexing, expanding, contracting, subjected to radar-absorbent material stress cycling, required the same class of solution that Fuller's team developed in 1963. Not the specific geometry. The principle: design the skin to work under operating conditions, not ambient conditions. Allow controlled movement rather than enforcing rigid constraint. If you've read Northrop Grumman's unclassified B-21 program histories, one detail stands out. The acknowledgement that titanium skin behavior under thermal cycling was a known problem going into the program, with known solutions derived from legacy programs. Legacy programs. The SR-71 is the legacy program they are referencing. A materials engineering crisis that nearly shut down a 1963 reconnaissance aircraft program is a direct ancestor of the manufacturing science behind America's current penetrating strike aircraft. The classified solution developed by Dick Fuller's team, declassified in the 1980s, published in technical literature in the 1990s, was available to B-21 engineers as established knowledge. The SR-71 flew operationally from 1966 to 1990. 32 aircraft built. No SR-71 was ever shot down by an adversary. Missiles were fired. None achieved intercept. The performance margins were sufficient. The aircraft worked at the conditions it was designed for. Will modern hypersonic programs face the same class of materials crisis the SR-71 did in 1963? The thermal and structural challenges of sustained hypersonic flight, Mach 5 and above, are an order of magnitude more severe than Mach 3.2. Comment: yes. If you think the lessons transfer, no. If you think the problem is categorically different. Dick Fuller returned to his stress analysis in week 4 of his 6-week window. The loose panel solution had been validated in accelerated fatigue testing. The cracking had stopped. He brought the data to Kelly Johnson. Johnson looked at the test results. He looked at Fuller. He approved the production change. 12 aircraft already in build were retrofitted. The manufacturing tooling was modified. The production line continued. The SR-71 first flew on December 22, 1964. It remained the fastest air-breathing aircraft ever built. As of July 2026, that record stands. The skin still leaks on the ground. The solution still works at altitude. The engineering knowledge it generated is still in use. The Blackbird did not just survive its materials crisis, it industrialized the problem.